Perfect. Can you hear me?
Yes.
With a name like Consolmagno, you were probably expecting a foreign accent, and you're getting a foreign accent, maybe not the one you were expecting. I'm here because I was sponsored by a group called Grasping the Nettle, which is a phrase that I had no idea what it meant. It sounded very painful, whatever it was. But I'm told it's a well-known phrase here, and if you want to know what it is, of course, you go to the internet, the font of all knowledge. Their point is to work on the dialogue between science and faith and to move from the confrontational God versus science to a relationship God and science. Of course, I know people in relationships where it's also confrontational, but that's and encouraging public dialogue. The important thing that I was told to emphasize, which I think is worth emphasizing, is that it is a multi-denominational outreach group that is trying to promote dialogue within and around the questions that only indirectly I'm going to discuss today. This is probably not going to be the talk you were expecting. I'm hoping it's also not the talk you were fearing. I have this great experiment that I like to talk about. I work in meteorites. I should mention, you know what meteorites are. They're the rocks that fall from the sky. And we have an estimate that maybe 5,000 to 10,000 hit the Earth every year, of which we are able to recover, if we're lucky, 5. Not 5,000, 5. Most of them fall in the ocean. Most of them don't fall in the ocean, fall in places where they look just like any other rock and you can't find them. Meteorites, when they are collected, if we're lucky, some of them wind up in our laboratory and then they wind up in meteorite collections. One of the great meteorite collections in the world is the one in the Natural History Museum in London. And instead of having a curator, they have a keeper. And the complaint of the people in the science world is that they take that name seriously, they keep them, they don't let you touch them. When I arrived at the Vatican Observatory in 1993, I had a background in meteoritics. I studied meteorites, mostly from a theoretical point of view. And I discovered there was a collection of 1,000 meteorites there with no curator. So I named myself the curator and gave myself permission to do experiments on them. Which is very handy. Our collection mostly came from the private collection of the Marquis de Rohan, and he collected them in the late 19th century the good old-fashioned way. He bought them. He died in the 1920s. His widow wanted to clear out the house, so she donated them to the Vatican, and we had this marvelous case where they were held. Now, the real question is, when I arrived, and I've got 1,000 meteorites, what am I going to do with these? They were a collector's collection. They're tiny bits of a little bit of everything, and not a whole lot of any one thing. What's more, I've been around the meteorite world long enough to know that there is some phenomenally good equipment being used that can take micrograms of material and analyze them basically atom by atom. This equipment already existed, so I didn't need to do that. And this equipment cost like $1 million, and I didn't have $1 million, so I certainly didn't need to do that. What I also knew was that in my previous life, before I arrived at the observatory, I in fact had been a theorist. Now, I don't know if you're familiar with it. About 10 years ago, there was a meeting of Jesuit scientists in Europe, all meeting in Italy. We had the meeting in English, but of course these are people from all over Europe speaking all sorts of languages. And after the meeting, we're sitting around in a bar doing what you do in a bar in Italy, drinking coffee. And one of the scientists out of nowhere says, "I hate terrorists. Terrorists never listen to you. Terrorists think they know everything. Terrorists are the most obnoxious." And it was 5 minutes before I realized he could not pronounce the TH. I used to be one of those theorists. And when I was making my models, I knew that there was a lot of input into the model that nobody had ever measured. Basic numbers about meteorites, like their density or their heat capacity. And if you're modeling how an asteroid is going to heat up or cool down, you need to know these things. So I thought, I've got the collection with a little bit of everything. Maybe I can make these measurements. Now, how do you make the measurements? I have no idea. I'm a theorist. So I asked, and it turns out there's a different $1 million machine. You take a very, very tiny, that is actually about half a millimeter across. It's a very small piece. And you put it into these $1 million machines, and they do fabulous jobs at making the measurements of, in this case, conductivity. But it takes all night to run one rock. And to make the rock work, you've got to cut it up into a tiny slice. And even I, giving myself permission, I don't want to cut up all my meteorites into tiny slices. What's more, meteorites actually are very heterogeneous. There are a little bit of this and a little bit of that, and what you have on one side of the rock may be very different from what you have on the other side of the rock, and who knows if you take a slice, whether it's going to be a typical slice or not. I needed a way to measure the heat capacity. What's heat capacity? Is the capacity to hold heat. How much heat does it take to raise the temperature by 1 degree? Or alternately, how much heat does it give off when it drops by 1 degree? And how do you measure this for a whole rock without destroying it? I was talking to somebody of mine, and one guy came up with the idea, so I ran with it. You take a thing of liquid nitrogen, a dewar, an insulated cup. If you look carefully, that's Buzz Lightyear on the other side. It's just we now have much more professional ones that say thermos on the side, and normally hold coffee. But it's named for a good Scotsman, Mr. Dewar. And you put liquid nitrogen in there, and the liquid nitrogen weight, if you put it on a scale and you measure the weight every 2 seconds, slowly drops as the nitrogen slowly boils away. It's at 70 degrees above absolute zero. And then you drop in the rock, and you saw what happened. Let me go back and see if I can make that happen again. You drop in the rock, and suddenly it boils like that. So the weight first goes up, and then it drops down really quickly. It goes up because of the weight of the rock, and it goes down quickly because of all the extra nitrogen being boiled off as the rock cools off, until finally the rock is at liquid nitrogen temperature, and that is the amount of liquid nitrogen that was boiled off, and I know how many calories it takes to boil a gram of liquid nitrogen, so I can tell how many calories came out of the rock during that drop, and I can work out what is the heat capacity of that rock. And it's pretty cool. You get to play with liquid nitrogen. Where do you get liquid nitrogen? Again, I'm a theorist. It turns out that the Vatican Observatory is located in the Papal Summer Gardens. It's not in Rome itself. It's about 30 kilometers south of Rome in the Alban Hills. And there's a palace there, and there's a couple of other big fancy. But in the far end of the gardens is actually a working farm, including a dairy farm. Now, I may be a city boy, but even I know that in order to get milk from a papal cow, you've got to have a papal bull. They don't use papal bulls anymore. I think the temptation for bad puns is too high. Instead, they use basically, bull semen that's been frozen in liquid nitrogen. So whenever we need liquid nitrogen, we just walk next door to the dairy farm with our dewar, fill it up, and then we've got all the liquid nitrogen we need. It turns out, of course, that there's lots of other problems that go into this. One is that when we had the container, you can see our thermos there and the scale in the computer. When you have it exposed to the air, water vapor will freeze on top of the liquid nitrogen, and that screws up the weights. So now I've got this other gizmo, that plastic thing that goes over the dewar. That I bought for €1 at a €1 store because it's made to hold dry spaghetti. It's great fun. It works. Some people worry about, is the liquid nitrogen going to, shatter the, you've all heard about, taking a flower and shattering it if it's really cold. What happens to your meteorites? If you want to break up an iron meteorite, you cool it down to liquid nitrogen temperatures. Isn't that going to harm the, I looked up the paper. If you want to break up an iron meteorite, you cool it down to liquid nitrogen temperatures, and then you hit it with a sledgehammer. As long as I keep the sledgehammers away, it doesn't hurt the meteorite at all. Now, you may ask, why am I doing this? Besides the fact that I get to play with the meteorites and get to play with the liquid nitrogen, of what possible use is this experiment? I'm enough of a theorist to know that there are a lot of places where we need to know the heat capacity of rocks. There's a particular weird and marvelous effect called the Yarkovsky effect, where if you have an asteroid that is spinning, the afternoon side is hotter than the morning side, and it emits higher energy infrared photons, and that gives an extra boost in one direction to either accelerate or decelerate the asteroid until it can move itself into a resonance point where then the gravity of Jupiter throws it into an Earth-crossing pattern. And it takes a long time, but we've got millions of years, hundreds of millions of years. To be able to calculate that, you have to know how much hotter is the afternoon side, and that depends on the thermal inertia, which depends on the heat capacity. So if there is, 400 years from now, an asteroid that looks like it might be getting onto a collision course with Earth that will hit the Earth and end all life, the numbers that I measure now might help us calculate just how big an effect that's going to be, how fast it's going to happen. But you know, and I know, that when I get up on Thursday morning, and I'm looking up, I really need to get up now, can I sleep another half hour? What is not going through my head is, if I don't make this measurement tomorrow, then all of life will die in 500 years on planet Earth. That actually doesn't go through my head. So why do I make these measurements? In effect, why do I want to get up on Thursday morning and go into the lab? Nobody's paying attention to whether I show up or not. I'm working at the Vatican, so I don't have to apply for grants, so I don't have to worry about getting renewal. I was talking to a scientist earlier, no committee, no grants, no proposals, no renewals. He says, how do I get in on this? You have to take a vow of celibacy. No one would know if I didn't show up. So what makes me show up? And it's actually a fundamental question, and that's the question I want to really address. But there's a bigger sense to the question. Why is anybody paying, why is the Vatican paying for an astronomical observatory? One of the great philosophers of our day asked that question of me.
Why does the Vatican have an astronomical observatory? For instance, you're the curator of meteorites at the Vatican. Why do they curate meteorites? Are they looking for the shooting star of David? What?
No, in fact, the whole idea of having astronomers really got started with the reform of the calendar back in the 1500s. And since then, just studying the universe is a great way to remind yourself that there's more important things in life than what's for lunch.
What is for lunch?
Never mind. I faced that question in a very different way when I was a postdoctoral fellow. My office was in that skyscraper there, the green building. It's not green, it was named for a guy named Green at MIT. And I'd walk across this bridge every day because I lived in one side and MIT was on the other. And then I go home at night and I was pushing 30 years old. And that was a crisis. 30! I'm getting old. Oh no. And I would work my tail off writing one of these theoretical papers on the evolution of the moons of Jupiter that 5 people in the world were going to read, and 2 of them were my enemies. And I go home at night wondering, why am I dedicating my life, especially when people are starving in the world? Why am I doing this? Of what possible utility is planetary astronomy, the moons of Jupiter? And I didn't have an answer. So, no problem so big you can't run away from it, I ran away. I quit science. I joined the U.S. Peace Corps. This is Kenya, 1983. I ran off to Kenya. Basically, I said, I'll go wherever you want me to go, and they said, we're sending you to Kenya. Great. We're going to have you teach high school science. Great. We're going to put you in a place where there's no windows in the windows and no black on the blackboards. I go, great. And after a few weeks of training, they say, maybe we're not going to send you there. Maybe we're going to send you to a better high school, one that does have windows. Whatever. Just as long as they wound up sending me to the best high school in the country that had a computer lab and lasers, and these kids were part of my astronomy club there. And this was for the visit of the president of Kenya, who showed up with his entourage of very important people. And they were explaining, with the astronomy that I taught them, why Kenya was a great place to build a space center, because you can launch things to the east, where you get the extra boost of the rotation of the Earth, you're on the equator, and you're launching over the Indian Ocean, so when the rocket blows up, it doesn't hurt your neighbor. And the president was very, very amused by all this, and the kids did a great job. The one kid who was the real spokesman, explained all of this to the president. And then as he's walking away, one of the entourage, a very stately, well-dressed woman, walks up to the kid and gives him a big hug. And the kid goes, "Oh, no, nothing for my friend." Because kids do the same all over the world. And within 3 months of being at that school, they said, no, in fact, we're going to move you to the university, and I wound up teaching astrophysics to graduate students at the University of Nairobi, which I could have been doing back in Boston. So in the meanwhile, I go every weekend up to my other Peace Corps volunteer friends, the ones who really were in the real Peace Corps, where there's no windows in the windows and no black on blackboards. And I bring my little telescope, and I'd have a slideshow. You can tell that was back when I was skiing and my hair wasn't gray yet. And everybody in the village would come and hear my talks about what NASA was discovering. And everybody in the village would come and look through my little telescope. And they'd look at the craters on the moon and go, wow. And they'd look at the rings of Saturn. How many people here have ever seen the rings of Saturn through a small telescope? Okay. How many of you who have seen the rings of Saturn have ever seen the rings of Saturn and not gone, oh, wow? Because that's what human beings do. Just like kids are the same all around the world, the rest of us are the same all around the world. And everybody wanted to know, what was NASA discovering, and what does this mean, and what, here are the big questions, and what have people been talking about? Because science isn't a bunch of numbers in a scientific paper. It's the conversation that we have in the hallways after the meeting, where we start to dream about what does this mean, what would it be like, how would we feel if we were visiting a moon of Jupiter, or what does this mean about who we are and where we come from? Or it just pulls us out of our day-to-day and makes us remember that there's more important things in life than just what's for lunch. Because as human beings, I had a cat when I was in Kenya, and my cat was much better at being a cat than I ever could be, but my cat never wanted to look through the telescope. Only human beings do that. Human beings have stomachs that need feeding. They also have souls that need feeding. We don't live by bread alone. I read that someplace. And suddenly I realized that's why you do astronomy even when people are starving in the world. because this is how we carry on the conversation that's been going on since Galileo, since Aristotle, since Romulus and Remus. And to be able to tell Africans, yeah, you can be part of that conversation too. Yeah, you can look at the Jupiter and be amazed at the things you see there, because you're human beings like the rest of us. And you have the right to dream, and you have absolutely the right to find out what everybody else has been dreaming about, and to be able to take part in that conversation. While I was in the Peace Corps, I was there with a group of about 80, mostly college kids, straight out of college. I was like 30, so I was the old guy. And in between teacher training and Swahili lessons, we played this game called tacky sack, where you got the little beanbag and you try to pick it up in the air and you pass it to the person next to you. Kind of the feel-good cooperative kind of game you would expect a bunch of volunteers to actually play. Well, one of the volunteers had a boyfriend from New York City who came to visit her during training. And he's watching this game and he goes, I don't get it. You don't knock the other person down so they can't hit you? You don't try to grab it and steal it? How do you win this game? Science is a lot like hacky sack. It's a game where you get status not by how much you've taken, but by how much you've given, how often your papers are cited. What is your goal? What is your ambition in science? Your first year, you think, someday I'm going to win the Nobel Prize. And by your fifth year, you're hoping that you get to go to the pepperoni pizza colloquium. That's the highlight of your week. What is the goal for you to be a scientist? How do you win this game? In order to get promoted at your university, it's great if you have the approval of others. Tenure, if I get tenure, I've won the game. If I get grant money, if I get awards, if I have fame, if I have successful students. These are all legitimate criteria to say, yeah, I've had a successful academic career. But are they ends in themselves? This is a paper, a page from Science, December 2013. Is your goal in life, is what gets you up on Thursday morning, the dangle, the carrot that says, someday I'm going to be able to be an at-al on a paper on the electric rearrangements of Brownian motion of colloids in pneumatic liquid crystals, which I looked up was actually cited 20 times in the next 3 years. Is that enough of a motivation to make you want to do the job? It's also interesting, if I just go back to this one, the way you win the game is to be able to do the game some more. If the game is its own reward, how do you win the game? Maybe the way to win is to not play. On the other hand, maybe you're motivated because you got great curiosity, because you love solving problems, because you love finding patterns, because you love the truth, because you love love. I don't know. If you were on the committee and you had to choose which person to promote, would you be looking for the one who has the approval of others or the one who has pleasure in finding patterns? If you are looking over a job, would you take a job that's likely to give you fame or a job that would be likely to allow you to satisfy your curiosity? And different jobs might have different outcomes. If you just love playing in the lab and you don't particularly care what you're doing, then you might work great in some industrial laboratory where they pay for the best sandbox possible. And you get to do the thing you love to do, which is fill with equipment. And where they've launch them is not up to you. It's where they come down that's somebody else's problem. It's not my department's syndrome if I'm wrong. Would you sacrifice anything on this list to get something on that list, or vice versa? Would you give up the approval of others to satisfy your own curiosity? The first time I presented data on the density of meteorites, one of the grand old men in the field came up to me and said, "Guy, why are you measuring meteorite density? Nobody does that." Because that's why I was doing it, because nobody had done it. But if I was depending on grant proposal success, I wouldn't go off in left field and do a kind of research that nobody was paying for. Would you give up tenure to do something that you love to do? That's easy to say if you don't have a wife and family to worry about, or a husband and family. Would you give up academic freedom, in other words, following your own curiosity, in order to be able to play in a really cool laboratory that some industry is paying for? Or vice versa? Would you give up fame? I'm never going to get the Nobel Prize measuring meteorite peak capacity. But I love the sense of finding patterns in those capacities. Would I give up grant money to search for the truth? Or would I give up truth in order to get grant money from the tobacco industry? Where is your heart? What motivates you to do the work? I'd say that's answering the question, where is your God? What kind of God is it that you're actually worshiping? Before you jump to a conclusion saying, "Oh, obviously I should be doing the noble thing," if you're not getting paid, you can't do the work at all. Let's be practical. If you don't do the science that the rest of the world is interested in, then you can't be part of the conversation that we call science. And at that point, you might just as well not be doing anything at all. Because science isn't just the numbers that we publish. It's the conversations in the hallway. And if nobody in the hallway wants to, they see you coming out of the hallway and they go, "Oh, it's him again." And I know scientists who have that effect when they show up at meetings, that people dodge into doorways to try to avoid talking to them because they've got some crazy hobby horse that nobody else is interested in. Why are you doing the work? And if you lost track of why you are doing the work, you wind up doing lousy work. Because you're doing it just because it's the only job you know. And guess what? You could be better paid and do more good for humanity working in the bank. Here's why I do the work. It's beautiful. It's beautiful. It's beautiful. It's beautiful. And these images give anyone the sense that it's beautiful. But it's even more beautiful if you know what's going on. I'm reminded of say, when you were a kid, you loved to watch football. Doesn't matter what kind of football. When you got a little bit older, you were able to play football, and then when you watched the game, you appreciated it all the more. And maybe as you got older, you got to be one of those players yourself that everyone else is watching, or maybe you got to be a sports reporter reporting. You do the names and backstories of each of the people out in the field. And that changes the way you see the game, but if you love the game, you still also love to watch it. As an astronomer, I look at the same stars as anyone else, but I know their names, and I know their histories, and I know there's a really cool thing going on there that's very mysterious, and someday I'm going to figure that out. And it gives this extra edge to looking at the stars. as a Jesuit, I'm affiliated with not only the world's largest or a chain of free hotels around the world, stay with other Jesuit communities, but I'm also connected with lots of schools and universities. And where a lot of people at small universities will take a sabbatical year to do science, to do research, because my life is full-time research, I would take a sabbatical year to teach, because I enjoy teaching. And one time I was teaching at Fordham University 8 years ago, and I was teaching Maxwell's equations. What are Maxwell's equations? Those are Maxwell's equations. And the great thing is, those are in integral form. You turn them into differential form, and you then take the derivative of one with respect to time and the other with respect to space, and you combine the terms and you order everything together. You wind up with a second-order differential equation where the change of the electric field with space is equal to a bunch of constants times the change of the electric field in time, or the same thing with the magnetic field. And I wrote all of this on the blackboard, and it's just lots and lots of math. I worn this shirt at the beginning of my term, and I told the kids, by the end of the semester, you'll know what all of those things stand for, and you'll get the joke. In case you can't read the shirt, it goes, and God said, Maxwell's equations, and there was light. So I did all of this change in space, change in time. I've written it all on the blackboard, and I'm about to spring on them the key to the joke, which everybody had forgotten by then, because I was not wearing that shirt. And a kid in the front row looks up at me and he goes, "Oh my God, it's a wave!" Yeah. I didn't have to point it out to him. He had realized that with these equations that, lots of different people had put together, Maxwell combined them in such a way that he suddenly realized that electricity and magnetism together have the capacity to generate a wave, and all those extra terms, when you add it up, turns out to tell you the speed of the wave, and it just so happened to be the speed of light. And a lot of people laughed at him. There was a guy in Germany named Mr. Hertz, who said, really, you say, if I can just jiggle the electricity back and forth on a wire and have another wire over here, suddenly there's going to be electricity running back and forth because there's a wave of electric field that made it move, and it works. And we call the frequency now the Hertz, based on him. And then there was an Italian named Marconi who said, if I do this and turn it on and off and on and off, then in every radius, the Italian word is radio, I can send a Morse code signal. By golly. Electricity and magnetism. This is also the set of equations that controls how power is transmitted across high tension wires, why we use alternating current. This is also the equation that explains why a light wave encountering a gas will have certain frequencies absorbed by the elements in the gas, and so that when we see its spectra 10,000 years later, because it's traveled through space, I can tell you what chemical elements it has experienced and what speed those elements were moving at relative to me, so that we get the expansion of the universe. And it's from the nature of these waves, ultimately, that we actually get both the principles of quantum physics and general relativity, but that would be another half hour to explain. That definitely was an oh my God moment. That sense of joy and that sense of oh my God is what permeates our experience of the universe. And it has since we started looking at the sky and wondering. Psalm 8, which dates from more than 2,000 years ago. You've set your glory above the heavens. When I look at your heavens, the work of your fingers, the moon and the stars, what are human beings that you're mindful of them? Mortals that you care for them. Yet you made us just a a little bit lower than God. How can this be? The church was interested in astronomy for a practical reason. It allowed you to figure out, all right, there's the new moon. It must be the beginning of the next Jewish month or Ramadan or whatever month you're worried about. And calendars got to be more complicated, so that eventually they needed to be repaired. That's the Vatican. That little building there is that tower. And in 1582, the tower was built with a little meridian line. Light comes through a hole in the south wall, and it moves as the seasons move. And from that, you can demonstrate that the calendar needed to be reformed, and Pope Gregory reforms the calendar. Not only to fix the slippage of leap years, but also so that we have a new way of calculating religious holidays. It turns out our religious holidays are not based on astronomy anymore, but on a clever mathematical formula that imitates. So that with the formula, you can actually calculate. This is Christopher Clavius, wrote this book in 1602 where he calculated the days of Easter until the year 5000. And according to this calculation, in 2020, Easter is going to occur on the 12th of April, which it is. There was a political reason to have astronomers at the Vatican. At the turn of the last century, 1891, Pope Leo XIII was eager to have the Vatican, which by then was reduced to just the area around St. Peter's, recognized as an independent nation. And one way of doing it was to promote a national observatory that would be accepted by other national observatories. At the same time, the end of the 19th century was the beginning of the myth that science was going to replace religion, and oh no, religion was all against science because it was afraid of being replaced. I don't want to go into that long story, except to say that everything you've learned about Galileo dates from the 19th century, and it's probably wrong. The truth about Galileo doesn't make the church look any better, but it was a different mistake than the mistake that people say it was. And it was promoted for political reasons. In America, it was to stop people with long names that ended in vowels, like Consolmagno, from getting into the country. Because these Italians and these Poles, horrible people. We have to keep them out because they're Catholics. And what do they know? They're ignorant. That kind of prejudice built into it. Just as a side note, one of the big drivers against the church in the 19th century was people who should have known better took the marvelous description of evolution that Darwin had come up with, which is a great description of how animals change over time, and decided to draw out of it lessons that were never there. I'm richer than you. It's only natural. If I weren't obviously superior to you, I wouldn't have been richer. And therefore, it's foolish for me to try to help you out as a poor person, because I would just be going against nature. It's only right that I'm richer. Not only that, but clearly you are an inferior person, and we have to make sure that we don't get any more like your type. And there were forced sterilizations, all in the name of what was called eugenics. And H.G. Wells thought this was a great idea. And all the great science popularizers before World War I thought this was a great idea. And it was only in the death camps of Nazi Germany that we began to see where it was all leading. And the one group speaking out against it was the church. So clearly the church was against this great scientific idea, which turned out to be junk science. Even if it had been good science, it would still be a bad idea, but it turns out it wasn't even good science. Anyway, to show that the church was not against science, just against junk science, the Pope decides to establish a Vatican observatory. And over the next 125 years, various popes have given their reason why astronomy was the kind of thing that the church would support. Pius XI, from no part of creation does there arise a more eloquent or a stronger invitation to prayer and adoration. So he's saying, as Leo XIII said, astronomy is good because it makes us look good. Pius XI says astronomy is good, not only because it makes us look good, but it incites us to be more religious. By the time you get to Pius XII, man ascends to God by climbing the ladder of the universe. Not only does it make me pray more, it is, in a sense, doing the work of prayer. And that's why we do astronomy. And then, John Paul II, actually science and religion are both needed for each other. Science purifies religion from error and superstition. Religion purifies science from idolatry and false absolutes. So we've gone from science being a nice PR gimmick to science having a role equal to religion. Benedict XVI, the laws of nature are an incentive to contemplate the works of the Lord with gratitude. And then Francis himself, scientific research can and should be a source of joy, a source of that oh my God moment. And while that's new to Pope Francis, it was also echoed in his namesake, the original Francis. Praise to you, my Lord, with all your creatures. Brother sun, who's the day, to whom you give us light, and he's beautiful and radiant and great, and bears a likeness to you, and that's the sun as seen from Mars. Praise to you through Sister Moon, wonderful eclipse. And the stars, in the heaven you find them clear and precious and beautiful. Praise to you, Brother Wind, through the air, cloudy and serene in every kind of weather. Praise to you, my Lord, through Sister Water, useful and humble and precious and chaste. Water coming out of the South Pole, the moon of Enceladus, orbiting Saturn. Praise to you, Brother Fire. You light the night, beautiful and playful, and robust and strong. Chesterton sums up this attitude. The essence of pantheism was that nature was a mother, but the point of Christianity is that nature is not our mother, nature is our sister, our brother. So the worshippers of Isis and Cybele, nature was a solemn mother. To Wordsworth, to Emerson, but to St. Francis, nature is a sister and even more a younger sister, a little dancing sister to be laughed at as well as loved. And this is the source of the love that causes us to want to do science. It's to be with my little sister, who I'm the youngest in my family, but my figurative little sister, that I go and work in the laboratory, making the measurements, teasing out point by point by point the heat capacity. And so I go to meetings with plots like this, and I can say, interesting, the theoretical heat capacity is systematically different from the actual measured heat capacity, probably because the theoretical heat capacity doesn't include effects like weathering. And maybe this is actually a way that I can quantify the weathering seen in a meteorite by comparing the theoretical against the measured. But more to the point, every one of those points was a rock I dropped into a dewar of liquid nitrogen. And it's holding a meteorite. It's liquid nitrogen. And it's finding a pattern. And every now and then when I look at this plot, I go, oh my God. Because it's in that joy. Every science needs, oh my God. Science only happens because of, oh my God. Both science and religion are conversations about the universe. They're ways of learning how we interact with this universe. It's not simply a question of is there a God, but there is a God, now what do we do? It's not just a question of there are a bunch of stars, but rather, why are there stars? How do they work? How does that tell us how things work here on Earth? The interaction that I see in my own life is that religion gives me the reason to do the science.
Back in the papacy before Francis was Benedict, and one of his lines in a final elocution to the fathers of the general congregation was, "Go to the frontiers." Well, there isn't much more frontier than 3.7 billion years away.
The first official interest of the Church for astronomy started in 1582 with the reform of the calendar. Then in 1891, Pope Leo XIII wanted to have an observatory to show that the Church is not against science, but the Church promotes good science.
They start out by having telescopes on the Tower of the Winds, and then on the walls surrounding the Vatican, as the city lights grow, and as the Italian government gives them back the territory out in Castel Gandolfo. In the 30s, they build new telescopes on the roof of the Papal Palace in Castel Gandolfo. Best telescopes of their era in the 1930s. By the 1980s, light pollution makes those telescopes unusable, so we build a new telescope in the dark skies of Arizona.
I'm Father Jean-Baptiste Kikwaya Eluo. I'm working in 3 projects. The first one is NEOS, Near Earth Object. So what I'm doing with NEOS is just observe them using our modern telescope VAT. The second project is meteors. I worked on very faint meteors, what we call shooting stars. And the third project is set fireball network. They will have 4 cameras here around Tucson so that actually we can monitor any fireball getting into the Earth atmosphere in the region.
This telescope, the Vatican Advanced Technology Telescope, it was the first of the new technology telescopes that has been considered pretty much the norm now in developing telescopes. With the advance of computer technology, we have the capability of bringing that advanced technology directly into our telescope. So it's an expandable, it's almost like it's a living machine, so it can grow as technology grows.
It is still very important to maintain scientific research at the Vatican, simply because there is still a lot of confusion about this relationship between science and faith. We are not out here trying to prove the existence of God by looking through a telescope. That's not what we're doing. But we can say that if we want to obtain any reasonable results looking through that telescope, we need to do it embracing a certain work ethics that is, in fact, the same work ethics that the Bible itself tells us through commandments and through the Gospels to embrace.
Human beings look at the stars and wonder. They want to know, what is that? What is that about? How do I fit in? They hear about the moon landing and they want to know, what was that like? If we're part of the human race, we're part of the race that went to the moon. We're part of the species that looked at the stars and wondered, what the heck are those things? Looking at the sky reminds you that there's more to the universe than what's for lunch. What's more, if you believe in a universe that God so loved that he sent his son, then not only are you going to want to study the universe because it's kind of cool, it's an act of worship. It's an act of getting closer to the Creator and getting closer to a universe, as St. Athanasius said 1,500 years ago, was cleansed and quickened by the Incarnation. Then, doing science is an act of worship.